Imagine that you are holding a handful of soil in your hand. Feel it. It is dense, moist, real. There are billions of organisms in that single gram. Bacteria, fungi, mites, microscopic roots, organic matter decomposing in stacked layers of chemical complexity. Now, imagine letting that soil fall, that it scatters, that each particle drifts away from the others until there are kilometers of emptiness between one and the next. Then, millions of kilometers. Then light years of absolute nothingness. And in that immensity, in that distance between one particle and the next, there exists something human beings have never stepped on, never breathed, never experienced in any direct way, except through the tiny and fading instruments of two machines that we launched there almost 50 years ago, and that are still transmitting, barely, from the other side of a boundary that most people do not even know exists. That place is interstellar space. And what I am going to tell you about it is not what you imagine. It is not the dark silence of science fiction films. It is not simply emptiness. It is something stranger, more violent, and more fundamentally hostile than any desert, ocean, or environment your brain has processed throughout its entire evolutionary history. It is the default state of the universe, the norm of which we are the exception. And understanding it changes forever the way you see the night sky. There is a structure that envelops our entire solar system, and very few people know about it. It has no name in popular culture. It does not appear in school textbooks. It is not mentioned in movies. Yet without it, life on Earth would be impossible, or at least radically different from anything that has existed over the past 4 billion years. It is called the heliosphere, and it is, in the most physical and measurable sense of the word, our cosmic home. The heliosphere is not a solid object. It is not a membrane or a layer of gas. It is the dynamic territory defined by the reach of the solar wind, that continuous stream of charged particles that our sun expels outward in all directions at speeds exceeding 1.5 million kilometers per hour. Every second, the sun ejects approximately 1 million tons of protons, electrons, and helium nuclei. It has been doing this without interruption for about 4.5 billion years, ever since hydrogen fusion ignited in its core, and it began its existence as a main sequence star. This wind does not simply disperse and vanish. It does something more important. It inflates. It creates a vast bubble of magnetized plasma that expands outward, pushing against the pressure of the gas and particles that fill the space between stars, the interstellar medium. The balance between that outward pressure and the inward pressure defines the size and shape of our cosmic bubble. In 1958, physicist Eugene Parker published a paper in the Astrophysical Journal predicting the existence of the solar wind. The proposal was so counterintuitive that both reviewers recommended its rejection. It seemed physically implausible to them that a star could continuously emit a stream of particles fast enough to reach the outer solar system. The journal's editor ignored those recommendations and published the paper anyway. A few years later, direct measurements from spacecraft confirmed that Parker had been right in all the essential details. The solar wind was real, it was omnipresent, and its existence reshaped what it meant to live in the solar system. The magnetic field lines carried by the solar wind twist into a spiral pattern as the sun rotates on its own axis, creating what astronomers call the Parker spiral. This magnetic architecture defines the environment of interplanetary space, guiding particles, modulating radiation, and creating the magnetic context in which Mercury, Venus, Earth, Mars, and all the bodies of the solar system exist and move. The sun's rotation speed at its equator is approximately 2 kilometers per second, and this rotation is what winds the field lines into that pattern that extends outward like the arms of a gigantic pinwheel, reaching the orbit of Earth, that of Saturn, that of Neptune, and far beyond. This magnetic field is not uniform. It has opposite polarities in the Sun's northern and southern hemispheres, separated by a thin layer called the heliospheric current sheet, which ripples through the solar system like the skirt of a spinning dancer. Spacecraft that pass through it record abrupt changes in the direction of the magnetic field. Low-energy cosmic rays are deflected differently on one side and the other. The heliospheric current sheet is one of the largest structures in the solar system, and it is completely invisible to any optical telescope. Within this architecture, there is something of vital importance. The heliosphere acts as a shield, not perfect, not absolute, but real and measurable. The main threat it defends against is galactic cosmic rays, high-energy particles, mainly protons, but also nuclei of heavier elements, accelerated to relativistic speeds by shock waves from supernovas and other violent processes scattered throughout the Milky Way. These cosmic rays flow through the galaxy in all directions, carrying energies capable of fragmenting atomic nuclei and breaking the molecular bonds of DNA. Without the heliosphere, they would bombard the inner solar system with significantly greater intensity. Estimates from NASA and the European Space Agency indicate that the heliosphere reduces the flux of galactic cosmic rays reaching the inner solar system by between 30 and 50% during periods of high solar activity. During the solar minimum, the reduction is smaller but still significant. If it were completely removed, the difference would measurably alter the radiation environment at Earth's surface, with consequences for atmospheric chemistry, mutation rates, and biological exposure over geological timescales. The mechanism by which the Sun modulates this protection is as elegant as it is complex. During years of maximum solar activity, the magnetic fields emerging from the surface are stronger and more organized, and the solar wind is denser and faster. These factors combined create a more effective barrier against incoming cosmic rays, not because it physically blocks them, but because it scrambles them. The spiral trajectories of the particles become so curved and so long within the heliosphere that many lose energy or change direction before reaching the interior. During the solar minimum, the field weakens, the wind thins, and more galactic particles penetrate. This cycle of approximately 11 years is precisely reflected in cosmic ray detectors on Earth's surface. When the Sun is quiet, the detectors record more. When the Sun is active, they record fewer. Every human civilization that has ever existed has done so within this protective bubble. Every scientific experiment, every work of art, every war, every birth, every death, all have occurred under the invisible umbrella of the heliosphere. All with exactly 2 exceptions. But before reaching those exceptions, it is necessary to understand the architecture of what the voyagers crossed. The heliosphere does not end abruptly, it transitions. But the transition is not what most people imagine. It is not a mist that gradually fades into darkness. It is a series of physically real boundaries, each marking a qualitative change in the conditions of the environment. To understand these layers is to understand what it means to be inside the protection of a star, and what it means to be outside. The first boundary is called the termination shock. Throughout the vast inner region of the heliosphere, the solar wind moves outward at supersonic speeds, typically between 300 and 800 kilometers per second, depending on solar conditions and latitude. Although it is extremely tenuous, only a few particles per cubic centimeter even near Earth, it moves with tremendous velocity and carries the Sun's magnetic field, maintaining the structure of the heliosphere through pure kinetic pressure. The termination shock is the point where the solar wind can no longer maintain that supersonic speed against the increasing pressure of the interstellar medium pushing inward. Here, the wind undergoes a dramatic deceleration, dropping from supersonic to subsonic speed within a relatively narrow transition zone. The physics is analogous to what happens when a fighter jet exceeds the speed of sound and creates a shockwave, but in reverse and on a planetary scale, a spheroidal structure that envelops the entire solar system. Voyager 1 crossed the termination shock in December 2004 at a distance of approximately 94 astronomical units from the Sun, about 14 billion kilometers from our home. The crossing was not a clean event. The spacecraft's instruments recorded multiple shock signatures over several days, suggesting that it crossed the boundary repeatedly as it rippled in response to fluctuations in solar wind pressure. The boundary was not a static line. It breathed. It flexed in real time. 3 years later, in August 2007, Voyager 2 crossed the termination shock at a notably different distance, about 84 astronomical units from the Sun. The discrepancy of 10 astronomical units, approximately 1.5 billion kilometers, revealed something fundamental about the geometry of the heliosphere. It is not a perfect sphere. The interstellar medium exerts greater pressure on the leading edge of the heliosphere, compressing it, while the trailing edge stretches backward to form a long tail. The heliosphere resembles a windsock more than a soap bubble, distorted by the motion of the solar system through the galaxy at approximately 26 kilometers per second. Beyond the termination shock extends the Helios Heath, a dense and turbulent buffer zone where the already decelerated solar wind accumulates, heats up, and churns. If the termination shock is the point where the solar wind hits the brakes, the Helios Sheath is the colossal traffic jam that follows. Solar particles here no longer move in a coherent outward flow. They slow down, compress, reach temperatures of millions of degrees, and flow sideways, gradually redirected toward the tail of the bubble, a structure known as the heliotail that extends away from the Sun in the direction opposite to the motion of our star through the galaxy. The Helios Heath is a strange and violent place, even by the standards of interplanetary space. Magnetic fields become tangled and disordered, losing the clean spiral pattern that characterizes the inner heliosphere. Voyager 1 spent nearly 9 years crossing this region, from late 2004 to mid-2012, traveling through conditions that no human instrument had ever sampled before. During that long transit, the probes detected something that no model had clearly predicted: regions of increased magnetic field intensity that appeared as discrete structures within the Helios Heath. Magnetic bubbles approximately 1 astronomical unit in diameter, formed by instabilities in the turbulent plasma. Scientists described them as a foam of magnetic islands, a zone where the Sun's magnetic field had fragmented into a chaotic cluster of independent cells. Once again, nature proved more disordered and more fascinating than any clean model devised from the comfort of an office on Earth. During those years in the Helios Heath, the instruments aboard Voyager 1 were also recording 2 trends that were converging towards something inevitable. The density of particles of solar origin continued to decrease. At the same time, the flux of galactic cosmic rays kept increasing. These 2 curves were moving toward an intersection, a point where solar particles would completely give way to galactic particles, where the influence of the Sun would be replaced by that of the galaxy. The scientists monitoring the data at the Jet Propulsion Laboratory knew that this point of intersection had a name: the heliopause. The heliopause is the outer boundary of the heliosphere, the surface where the outward pressure of the solar wind finally reaches equilibrium with the inward pressure of the interstellar medium. Crossing this line means leaving the Sun's magnetic domain. It means no longer being surrounded by particles that originated in our star. It means entering a region governed by galactic conditions, where the local interstellar magnetic field replaces the solar field, where interstellar plasma takes the place of the solar wind, and where galactic cosmic rays arrive without the protective filtering of any star. Voyager 1 crossed the heliopause around August 25, 2012, at a distance of approximately 121 astronomical units from the Sun. That is equivalent to about 18 billion kilometers. It was the first time in history that an object built by human beings left the domain of its parent star. The crossing was not recognized immediately. The data traveled at the speed of light, but even so, they arrived with a delay of approximately 17 hours. And when they did arrive, they told a story that required months of careful, sometimes controversial, analysis to be fully interpreted. The cosmic ray detector was the first to speak clearly. On August 25th, the galactic cosmic ray count made an abrupt jump upward, approximately 9% above the already elevated levels measured in the outer Helios heath, and substantially above the values recorded deep within the heliosphere. Simultaneously, the flux of low-energy solar particles dropped to nearly zero. Together, these two signals painted an unmistakable picture. The spacecraft had left the Sun-dominated zone. But the magnetometer told a different story, or seemed to. Many models had predicted that the direction of the magnetic field would rotate substantially at the heliopause, shifting from the Parker spiral orientation to the orientation of the local interstellar field. Voyager 1 recorded a change in intensity and some variation in direction, but not the dramatic rotation that some theorists had expected. This discrepancy fueled months of intense scientific debate. Had it truly crossed the heliopause, or had it simply entered an anomalous region within the Helios heath? The situation was genuinely uncertain because the space at the boundary between the heliosphere and the interstellar medium turned out to be more complicated than any previous model had represented. The simulations that theorists had built over decades assumed relatively clean transitions, relatively uniform local properties, and relatively predictable dynamics. The actual data from Voyager 1 suggested that the boundary was more like a battle zone than a line of demarcation. Magnetic filaments from the heliospheric interior intertwined with structures from the interstellar field. Particle flows did not follow the expected patterns. The physics of the boundary was, as so often in the history of science, considerably richer than any earlier model. The resolution came from a completely unexpected source. In early 2012, a powerful solar eruption had sent a shockwave propagating outward through the heliosphere. 13 months later, in April 2013, that disturbance reached the position of Voyager 1 and caused the tenuous surrounding plasma to oscillate, producing detectable electron density waves. The plasma wave instrument on board recorded those oscillations, and their frequency allowed scientists to directly calculate the density of the surrounding plasma. The result was approximately 0.055 electrons per cubic centimeter, a density much higher than what would be expected inside the Helios heath, and consistent with the density predicted for the local interstellar medium. This number settled everything. Voyager 1 was not in an empty pocket of the Helios heath. It was in interstellar space. This result, published in the journal Science in 2013 by a team led by Don Gurnett of the University of Iowa, marked the definitive close of the debate The plasma density was the decisive piece of data, the kind of measurement that does not admit reasonable alternative interpretations. A density of that value, in that context, could only originate from the interstellar medium. Voyager 2 would provide an even more definitive confirmation when it crossed the heliopause on November 5, 2018, at a distance of approximately 119 astronomical units. Crucially, Voyager 2 carried a functioning plasma science instrument, a device that directly measures the temperature, density, and velocity of charged particles in the surrounding environment. The equivalent instrument on Voyager 1 had failed in 1980, decades before its historic crossing, depriving scientists of the most direct measurement possible during that first historic passage. The plasma instrument on Voyager 2 performed perfectly. The data showed a sharp and unequivocal transition. Inside the Helios heath, the plasma was hot, between 30,000 and 50,000 Kelvin, and was composed predominantly of protons and electrons from the solar wind flowing outward at reduced speeds. On the other side of the boundary, the plasma temperature dropped sharply, the density increased, and the composition changed to interstellar material, mainly neutral and ionized hydrogen that did not originate from the Sun, but from the broader galactic environment. In addition to temperature and density, the Voyager 2 plasma instrument measured something equally revealing: the flow velocity. Inside the Helios heath, particles still flowed predominantly outward, in the radial direction from the Sun, although at considerably lower speeds than in the inner solar wind. Outside the heliopause, that radial flow disappeared. Particles in the local interstellar medium did not move in any preferred direction relative to the Sun. They moved with the velocity of the interstellar medium at relative rest, reflecting the local currents of galactic gas rather than any solar influence. The signature of the Sun in the motion of the plasma had disappeared completely. The change occurred within a distance smaller than the separation between the Earth and the Sun. This deserves emphasis because it dismantles one of the most common misunderstandings. Many people imagine the boundary of the heliosphere as a gradual fading, a long and slow transition unfolding across billions of kilometers. The Voyager data showed the opposite. The heliopause is thin. The change is sharp. On one side, the Sun governs. On the other, the galaxy takes control. The contrast is absolute and occurs over a distance that even our slowest spacecraft in the solar system would take only weeks to cross. A later analysis published in 2019 in Nature Astronomy, using data from both probes simultaneously, revealed that the heliopause is not completely static. Its position fluctuates by tens of astronomical units in response to changes in solar activity over the 11-year cycle. During periods of high solar activity, the denser and faster solar wind pushes the heliopause outward. During solar minimum, the boundary contracts slightly inward. The distinction between 119 and 121 astronomical units in the crossings of the two voyages reflects in part this dynamic variability, as well as the geometric asymmetry of the heliosphere caused by the motion of the solar system through the local interstellar medium. The heliosphere does not fade away. It ends. It breathes as it ends. But it ends. This is where it becomes necessary to make a distinction that most people have never considered, because it addresses one of the most frequent misunderstandings about where interstellar space begins and what it truly means to be part of the solar system. When most people hear the term solar system, they think of the Sun and its family of planets, moons, asteroids, and comets. The outermost recognized planet, Neptune, orbits at about 30 astronomical units. The Kuiper Belt, home to Pluto and thousands of icy bodies, extends to approximately 50 astronomical units. Beyond that, astronomers believe there exists the Oort cloud, a hypothetical sphere of icy objects that could extend from about 2,000 to 100,000 astronomical units from the Sun. Objects in the Oort cloud are still gravitationally bound to our star. They orbit the Sun in periods of millions of years, nudged by the weak gravitational influence of nearby stars and the slow tidal pull of the Milky Way. This means that the gravitationally defined solar system extends enormously far, possibly 1 or 2 light years from the Sun in all directions. The heliopause, by contrast, lies at about 120 to 140 astronomical units, which is equivalent to less than 2/1000ths of a light year. The heliosphere occupies a tiny fraction of the Sun's gravitational domain, less than 1/10,000th of the volume enclosed by the outer boundary of the Oort cloud. This creates a situation that is both a physical reality and something philosophically unsettling. Objects in the Oort cloud still form part of our solar system in the gravitational sense. They still orbit the Sun, but they exist outside the heliosphere, completely immersed in interstellar space. They do not have the solar magnetic shield. They are bombarded by the full flux of galactic cosmic rays. They float in interstellar plasma. For all practical environmental purposes, they are interstellar objects that happen to be gravitationally tied to a distant star. Interstellar space, therefore, does not begin at the edge of the solar system's gravitational influence. It begins much closer. It begins at the heliopause. And everything that lies beyond that thin membrane exists in a fundamentally different physical environment, regardless of whether it remains gravitationally bound to the Sun. This distinction matters because it reveals the true nature of the heliopause. It is not an abstract demarcation. It is a boundary of survival. The gravitational boundary of the solar system is an imaginary surface, a mathematical concept that defines the point where the Sun's attraction yields to that of a neighboring star. Crossing it changes nothing on the physical level. It cannot be felt. Instruments record no alteration. But the heliopause is completely different. Upon crossing it, the magnetic environment transforms. The particle population changes drastically. Radiation exposure shifts. The energetic landscape becomes something else. An object that crosses the heliopause experiences a genuine and detectable transformation in its physical circumstances. An object that crosses the gravitational boundary perceives absolutely nothing. This is what made the Voyager crossings so scientifically momentous. They were not symbolic milestones or arbitrary lines drawn on a map. They were the first direct measurements of a real physical transition. The first time an instrument built by human beings had sampled the interstellar medium and sent the results back. And what it found was sobering. For centuries, a single word has limited our understanding of the cosmos: void. It appears in textbooks, in documentaries, in the everyday language of even professional astronomers when they describe the regions between the stars. The void, nothingness, the inert darkness stretching from one sun to another. This description is not entirely incorrect, but it is so catastrophically incomplete that it promotes a mental image of interstellar space that ignores virtually everything that is real, dangerous, and physically relevant about the environment that occupies the vast majority of our galaxy. Beyond the heliopause, in the region that Voyager entered, and whose properties it confirmed through direct measurements, there is something. That something has density, temperature, and chemical identity. It possesses magnetic architecture and dynamic behavior that evolves on timescales of millions of years. Scientists call it the interstellar medium. And to understand its true nature, it is necessary to abandon almost all preconceived ideas about how matter ought to behave. Let us begin with the most fundamental quantity: how much matter actually exists between the stars. At Earth's surface at sea level, every cubic centimeter of the atmosphere surrounding us contains approximately 25 trillion molecules. This number, 25 followed by 18 zeros, represents a concentration of matter so dense that molecules collide with one another billions of times per second. This density is what gives air its substance, its resistance, its ability to transmit sound and scatter sunlight into a blue sky. You can feel the air on your skin. It is tangible. Now jump to the most extreme vacuum conditions that human engineering has ever managed to produce. In specialized laboratory chambers designed for surface science and spaceflight simulation, physicists can reduce the number of particles to about 100,000 molecules per cubic centimeter. These are the emptiest environments ever created on our planet. 100,000 particles per cubic centimeter is our technological limit. Now consider interstellar space. In the diffuse regions that occupy the volume between the stars of the Milky Way, the average particle density is approximately 1 atom per cubic centimeter. 1. A solitary hydrogen atom drifting in a volume the size of a sugar cube. In certain areas, the density increases modestly to 10 or perhaps 100 atoms near the edges of cold molecular clouds. In others, particularly in the vast hot cavities generated by ancient supernova explosions, the density plummets to 1/100th of an atom per cubic centimeter or less. At those concentrations, one would have to sample 100 sugar cube-sized volumes before encountering a single particle. The ratio between Earth's atmospheric density and that of the typical interstellar medium is not measured in thousands or millions. It is a factor of roughly 25 trillion. This gap exceeds the ratio between a single raindrop and all the water in Earth's oceans. It belongs to that category of numbers that are comfortable in equations but resist being fully absorbed by the human mind. No metaphor can honestly encompass this abyss. And yet, this near-nothingness is not without structure. Scientists have identified several distinct states in which interstellar gas exists, each characterized by radically different temperatures and densities. The cold neutral medium, relatively speaking the densest stable phase of diffuse interstellar gas, reaches concentrations of 20 to 50 atoms per cubic centimeter, with temperatures ranging from 80 to 100 Kelvin, approximately between -190 and -170 degrees Celsius. Hydrogen atoms in these regions move very slowly, almost drifting through space. It is in the cold neutral medium where star formation begins. When enough cold gas concentrates within a single gravitational well, the internal thermal pressure can no longer counteract the attraction, triggering the collapse that will form new stellar systems. However, this cold and dense phase occupies only between 2 and 4% of the galactic interstellar volume. The process that leads from those cold concentrations of gas to stars like the Sun is neither simple nor fast. Gravity pulls the gas inward, but thermal pressure and internal turbulence resist. The galactic magnetic field also plays a role. Magnetic fields that penetrate cold clouds transfer angular momentum to the rotating gas, slowing the collapse and allowing density to increase more gradually. In the final stages, when the collapsing core reaches densities high enough to become opaque to its own radiation, heating accelerates and nuclear fusion eventually ignites. What was born in the cold neutral medium becomes the kind of object that creates and maintains its own heliosphere. Far more significant in terms of volume is the warm neutral medium. where temperatures rise to between 6,000 and 10,000. Kelvin and densities fall to between 0.2 and 0.5 atoms per cubic centimeter. This medium occupies between 30 and 40% of the volume of the galactic disk, forming the backdrop against which colder clouds and hotter cavities are scattered. It is precisely this phase that the Voyager probes encountered after crossing the heliopause. The local interstellar cloud, the specific parcel of interstellar gas through which our solar system is currently traveling, consists primarily of warm, partially ionized gas at temperatures near 7,000 Kelvin, with a density of approximately 0.2 atoms per cubic centimeter. This local interstellar cloud, with which the solar system has been interacting for tens of thousands of years, is one of several similar structures that form the local interstellar cloud complex, a group of tenuous gas regions located within the local bubble. Ultraviolet spectroscopy studies carried out with the Hubble Space Telescope, observing the light of nearby stars that passes through the local medium before reaching us, have made it possible to map the composition, temperature, and velocity of these clouds in remarkable detail. It is known that the local interstellar cloud is moving toward the solar system at about 26 kilometers per second, the same speed at which the solar system is moving in the opposite direction. Within less than 10,000 years, the Sun may have left this cloud and be traveling through a different region of gas, or even through the emptier interior of the local bubble. When that happens, the properties of the immediate environment outside the heliopause will change in detectable ways. Hotter and even more rarefied is the warm ionized medium, where temperatures rise to between 8,000 and 12,000. Kelvin and ultraviolet photons from young massive stars have stripped electrons from hydrogen atoms, turning the gas into a plasma of protons and free electrons. This ionized gas responds to magnetic fields, generates electric currents, and emits radiation at characteristic wavelengths, the reddish glow of H-alpha emission that astronomers can detect across thousands of light years. It occupies approximately between 20 and 25% of the volume of the galactic disk. But the phase that dominates the total volume of the galaxy is also the most extreme, the hot ionized medium. This is gas heated to temperatures of 100,000 to 10 million Kelvin, with some regions exceeding even that astonishing figure. Despite these furnace-like temperatures, the density drops to values between 1 and 0.1 atoms per cubic centimeter. This superheated plasma fills the enormous cavities of the interstellar medium, regions sculpted by the accumulated violence of massive stellar evolution. The origin of these cavities lies in supernovae. When a star with a mass greater than about 8 times that of the Sun exhausts its nuclear fuel, it collapses and explodes, releasing approximately 10 to the power of 44 joules of kinetic energy into the surrounding gas. This amount of energy is difficult to conceive. A single event releases as much energy as the Sun will produce over its entire 10 billion year lifetime. The resulting shockwave expands at thousands of kilometers per second, sweeping up the interstellar gas like a snowplow, compressing it into a thin expanding shell and leaving behind an interior cavity of extremely hot, diffuse plasma. The newly formed supernova remnant shines brightly in X-rays for tens of thousands of years as the hot gas trapped inside it gradually cools. As the outer shockwave advances into the surrounding interstellar medium, it can compress the cold gas it encounters and in some cases trigger the formation of new stars along its advancing edge. The violence of stellar death becomes, paradoxically, the midwife of stellar birth. In regions where massive stars cluster, the combined effects of stellar winds and successive supernovae produce structures on an even larger scale. superbubbles. These can extend hundreds of light years and remain at extreme temperatures for millions of years, continuously reinflated by the energy of new explosions. Some models suggest that these superbubbles interconnect, forming a network of hot tunnels that could constitute between 50 and 70% of the total interstellar volume. Our own solar system lies within one of them. The local bubble, as it is called, is a region of anomalously low density and elevated temperature about 300 light-years in diameter. It was carved out by a series of supernovae that occurred within the last 10 to 20 million years, presumably in the Scorpius-Centaurus Association. In January 2022, a paper published in Nature determined through observations and three-dimensional modeling that the expansion of the surface of this local bubble was responsible for the formation of all nearby young stars, including those in the Pleiades cluster and the Taurus molecular cloud. We have spent several million years traveling through this structure, inhabiting the exception created by the violence of suns that died long ago. The local bubble is not a perfect or smooth cavity. Its interior is permeated by tenuous gas at temperatures of 1 to 3 million Kelvin, visible in soft X-ray emission. Its outer wall is formed by a dense layer of cold gas and dust, the swept up and compressed residue of all the material that the shock waves from those supernovae pushed aside as they traveled. This wall is the surface upon which several of the youngest stars in our galactic neighborhood are forming right now. The founding violence of the bubble, concentrated millions of years ago, continues to generate observable consequences today. And yet, what the temperature of that environment suggests at first glance is radically different from what anything immersed within it would actually experience. A region at 10 million Kelvin sounds as though it should incinerate anything that touches it. In our terrestrial experience, temperature means heat. Heat means danger. Danger means destruction. An object in such an environment on Earth would vaporize in a fraction of a second. But physics tells us something counterintuitive that completely transforms this picture. Temperature measures the average kinetic energy of individual particles, not the total thermal energy transferred to a surface per unit time. When those particles are separated by meters or kilometers, as in hot interstellar plasma, the frequency with which they impact any surface is so low that it becomes completely insignificant. A spacecraft immersed in the hot, ionized medium would not heat up from its surroundings. Individual particles would strike the hull at extraordinary speeds, each delivering a minuscule amount of energy. But the intervals between those impacts would be so long, and the energy per impact so small relative to the spacecraft's total thermal budget that the net effect would be imperceptible. Meanwhile, the spacecraft would radiate its own thermal energy into the surrounding vacuum in the form of infrared photons, losing heat faster than the sparse plasma could replenish it. The real experience would be one of relentless and inescapable cold. In interstellar space, temperatures of millions of degrees and functional freezing coexist within the same cubic meter. The physics is correct. The experience is the opposite of what the numbers seem to promise. But there is one component of the interstellar medium that deserves special attention, not because of its dominance in mass or volume, but because of its disproportionate effects despite its almost unimaginably small abundance. Interstellar dust. This is not the dust motes visible in a beam of sunlight. Interstellar dust grains are microscopic solid particles, typically between a few nanometers and a few tenths of a micrometer in diameter, smaller than a wavelength of visible light. They are composed mainly of silicate minerals and carbonaceous compounds, tiny fragments of rock and soot. Their origin lies in the outer atmospheres of evolved stars, particularly red giants, where conditions allow solid particles to condense from cooling stellar outflows. Supernova explosions also produce and distribute this dust, seeding the interstellar medium with newly forged solid material. The number density of interstellar dust is almost absurdly low, approximately 1 grain for every 100,000 cubic meters. A microscopic speck floating alone in a volume equivalent to that of a large residential building. And yet, these almost ghost-like particles produce effects that have shaped the observational history of astronomy and the chemical evolution of the galaxy. The prominent dark band that appears to divide the bright arc of the Milky Way is not an absence of stars. It is a curtain of interstellar dust between us and the billions of stars beyond, absorbing their visible photons and re-emitting that energy at infrared wavelengths invisible to the human eye. For more than a century, this extinction of starlight confused astronomers, leading them to underestimate galactic distances and misinterpret the structure of the Milky Way. Only with the development of radio astronomy and infrared astronomy was it possible to see through the veil. But dust does not only conceal, it also builds. Under the conditions of extreme dispersion in interstellar space, atoms in the gaseous phase encounter one another so rarely that chemical reactions between them are practically non-existent. 2 hydrogen atoms could wander for millions of years before passing close enough to allow a reaction. But when an atom lands on the surface of a dust grain, it can adhere to it, migrate across it, and encounter other absorbed atoms with which to react. The surface of the grain acts as a catalyst and meeting point, dramatically accelerating reactions that would be impossible in the gaseous phase. The most important reaction of this type is the formation of molecular hydrogen, the essential fuel for gravitational collapse and the birth of new stars. Without the catalytic function of these dust grains, the supply of molecular hydrogen in the galaxy would be drastically lower, and star formation would come to a halt. By the mid-2020s, astronomers had identified more than 270 distinct molecular species in interstellar and circumstellar environments. Simple molecules such as carbon monoxide and the hydroxyl radical are common. More complex molecules such as formaldehyde, methanol, acetaldehyde, and even amino acid precursors such as glycine have been detected in cold, dense molecular clouds. Polycyclic aromatic hydrocarbons, large ring-like carbon structures, appear to be ubiquitous in the diffuse medium, producing characteristic infrared emissions that astronomers detect throughout the galaxy and beyond. The interstellar medium has physics, it has chemistry, it has structure on scales ranging from the submicrometric dimensions of individual grains to the tens of parsecs of superbubbles. It is a subject that fills scientific journals and sustains entire research careers. None of this changes a fundamental practical reality. 1 atom per cubic centimeter is not a resource. It is the ghost of a resource. A magnetic field of a few microgauss stretched across light years of emptiness is not a shield. It is a structural feature of the vacuum itself. Dust grains separated by distances greater than concert halls are not raw material. They are isolated motes drifting in a desert that makes the Sahara look like an ocean. Cosmic rays arriving from every direction at all times are not an inconvenience. They are an unceasing assault, with no refuge anywhere in the medium capable of stopping them. These cosmic rays deserve their own chapter. They are not electromagnetic rays. The name is a historical artifact from the early 20th century, when their nature was a mystery. They are material particles. The vast majority, about 87% of the total flux, are protons. Helium nuclei make up around 12%, and the rest are heavier ions. They have been accelerated to extraordinary speeds by astrophysical shockwaves mainly those generated by supernova explosions propagating through the interstellar medium. The acceleration mechanism is elegant and brutal. The expanding shockwave of a supernova creates a shock front where the speed of the gas drops from supersonic to subsonic. Nearby charged particles can bounce back and forth across this boundary, gaining energy with each crossing in a process called diffusive shock acceleration. The particle approaches, is deflected by turbulent magnetic fields on one side, crosses the front, is deflected again on the other side, crosses back, and accumulates energy with every transit. After thousands of years of repeated crossings, a single proton can reach energies exceeding 10 to the 15th power electron volts, far beyond what any particle accelerator built by human beings can achieve. It is worth pausing for a moment to consider what this means in terms of natural engineering. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built by humanity, can accelerate protons to energies of about 13 trillion electron volts. That is 13 times 10 to the 12th power. The most energetic cosmic rays detected at Earth's surface carry energies of 10 to the 20th power electron volts, more than 10 million times greater than the maximum capacity of the LHC. The universe builds accelerators whose results make our best technological efforts look like toys. Once launched into the interstellar medium, these energetic particles do not travel in straight lines. The galactic magnetic field curves their trajectories, forcing them to spiral along field lines, with radii determined by their energy and the strength of the local field. Magnetic irregularities permeating the interstellar medium continuously scatter them, randomizing their directions over time. The result is that cosmic rays, originating in point sources such as supernova remnants, become completely mixed throughout the galaxy over tens of millions of years. They arrive at any given point from virtually all directions simultaneously. Their angular distribution is isotropic to an extraordinary degree. It is not possible to point to a cosmic ray and trace its origin, because its trajectory has been scrambled beyond recovery by millions of years of magnetic deflections. There is one partial exception: ultra-high energy cosmic rays, those exceeding 10 to the 18th power electron volts, known as the Ankel energy of the spectrum because of the characteristic shape of the flux curve at that energy. These particles are so energetic that the galactic magnetic field cannot significantly bend their trajectories. They travel approximately in straight lines through the galaxy, which in principle makes it possible to trace their origin. The problem is that they are extraordinarily rare. Only about one cosmic ray of this energy arrives per square kilometer per century. Building sufficient statistics to identify sources requires detectors the size of small countries, such as the Pierre Auger Observatory in Argentina, which covers 3,000 square kilometers. And even so, after decades of observation, the origin of the highest energy events remains a subject of active research. The energy spectrum of cosmic rays is astonishing. At the lower end, particles with energies of hundreds of millions of electron volts, comparable to the protons of a medical cyclotron. At the upper end, ultra-high energy cosmic rays exceed 10 to the 20th power electron volts. A single proton can carry the kinetic energy of a baseball thrown at nearly 100 kilometers per hour. The flux decreases drastically as energy increases. But even the moderate energy population that arrives continuously from all directions creates a constant and relentless radiation environment with no equivalent inside the heliosphere. And when these particles encounter matter, the process of destruction they trigger is extraordinarily sophisticated and extraordinarily dangerous. Imagine a single cosmic ray ion, an iron nucleus stripped of its 26 electrons, traveling at 95% of the speed of light, with a kinetic energy exceeding 10 billion electron volts. It approaches the aluminum hull of a spacecraft. From the instant it penetrates the metal, it begins to interact with the electron clouds of the atoms it encounters. Its enormous charge and velocity tear electrons from one atom after another along its trajectory, depositing energy in a dense and narrow trail. This process, known as energy loss by ionization, heats the material to extreme temperatures on the molecular scale. In biological tissue, that ionization trail is devastating. The released energy disintegrates molecular bonds in a corridor only nanometers wide, but capable of extending centimeters in length. The result is a scar of chemical destruction so concentrated and linear that cellular repair mechanisms are often unable to correct it. The lesion does not resemble any form of radioactive damage that terrestrial biology has faced in the evolutionary history of life. It is not diffuse like the gamma radiation from a nuclear explosion, nor localized like the energy of an alpha particle. It is a track, a line of molecular destruction that passes through the interior of a cell from side to side. Radiobiological studies with heavy ions accelerated in facilities such as the Brookhaven National Laboratory in New York or the Heavy Ion Medical Accelerator in Chiba, Japan, have documented that this type of damage produces complex chromosomal aberrations that DNA repair mechanisms not only fail to correct, but sometimes worsen when attempting to join the wrong fragments. The result may be cell death, cancerous transformation, or the transmission of mutations to daughter cells. But this trail of ionization is only the beginning. As the iron nucleus advances, the probability of a direct impact with an aluminum nucleus increases. When this happens, the collision is catastrophic for both particles. Both nuclei shatter in a process called spallation. The fragments include free protons and neutrons, lighter nuclei such as helium, lithium, and beryllium, and unstable particles called pions that decay almost instantly into gamma rays and other particles, generating a flash of electromagnetic radiation at the point of impact. Neutrons, lacking electrical charge, are projected outward without being deflected by electron clouds, penetrating much more deeply than charged particles. They in turn interact with other nuclei along their path, potentially triggering additional spallation events and creating a branching network of tertiary particles. This phenomenon is known as a hadronic cascade, and a single incident iron nucleus can generate hundreds of secondary particles in the first centimeters of material, which in turn can produce hundreds more. The cascade expands like a lethal rain, transforming a single extremely high-energy particle into a spray of lower-energy particles distributed across a much larger volume. And some of those secondary particles turn out to be biologically more damaging per unit of energy than the original cosmic ray. This creates the fundamental paradox of shielding against space radiation. For lower-energy cosmic rays, shielding works as intuition suggests. The material absorbs the particle and the threat is neutralized. But for the high-energy heavy ions that constitute the greatest biological risk, thicker shielding can actually increase the total radiation dose experienced inside. The incident particle is stopped, yes, but the cascade it generates produces a more diffuse radiation field that is, in certain respects, more harmful to anyone sheltering behind it. Optimal shielding strategies employ hydrogen-rich materials such as water or polyethylene, which produce fewer heavy secondary fragments, because when a cosmic ray collides with a hydrogen nucleus, a single proton, rather than with an aluminum nucleus containing 13 protons and 14 neutrons. The resulting fragments are far fewer and less massive. Less mass means less cascade. But even these materials offer diminishing returns beyond a certain thickness, and the mass penalty involved in carrying sufficient shielding for a decades-long journey adds enormously to propulsion requirements that already operate at the limits of what is conceivable. Researchers at NASA and ESA have spent decades studying this problem as part of preparation programs for crewed missions to Mars. Their conclusions are consistently discouraging. No passive shielding solution that is viable in terms of mass can reduce exposure to galactic cosmic rays to levels considered safe for long-duration missions. For a 40-year journey through interstellar space, the problem has no known solution with the physics and materials that exist today. And this is where everything converges on a question that cannot be avoided. Knowing the composition of interstellar space and understanding what it means to exist within it are two fundamentally different things. Everything described up to this point has been the language of a physicist, cataloguing phases, measuring densities, tracing magnetic architectures. Everything is precise. Everything matters scientifically. But none of it answers the question that truly haunts the human imagination when we look at the night sky and marvel at the stars. Could we ever reach them? The answer is not a simple no. It is something worse than a no. It is a cascade of physical constraints, each independently formidable, that combine to produce a barrier so complete that it challenges the limits of what any technology, no matter how advanced, could plausibly overcome. Interstellar space does not block travel with a wall. It blocks it with three adversaries: distance, deprivation, and time. Let us begin with energy. Within the solar system, energy is abundant. At Earth's orbital distance, the solar flux delivers approximately 1,360 watts per square meter. A surface the size of a dining table, oriented directly toward the sun, receives enough energy to power a small home. Even at Jupiter, 5 times farther away, solar panels still generate useful electricity. The Juno probe operates entirely on solar power at Jovian distances. But solar intensity obeys the inverse square law. Doubling the distance from the sun reduces the flux to 1/4. By the time one reaches Neptune's orbit, 30 astronomical units from the sun, the flux has decreased to approximately 1/900th of its value at Earth. At the heliopause, 120 astronomical units away, it is less than 1/14,000th of what our planet receives. And these distances are still cosmically trivial compared with the voids between the stars. At a distance of 1 light-year from the sun, the solar flux has been reduced to approximately 1/4 billionth of its value at Earth, barely a few 10 millionths of a watt per square meter. To generate even a single watt of electricity at this distance, even with the most optimistic efficiency of solar panels, one would need an array with a collecting area rivaling the footprint of a large international airport, just to light a single bulb. At the distance of the nearest star, more than 4 light-years away, the sun would be nothing more than a moderately bright star in an unfamiliar sky. Its energy contribution to any spacecraft in the vicinity would be indistinguishable from zero. This creates a problem that has no analogue in the entire history of human exploration. Every journey undertaken by our species has occurred in an environment that in some way offered the possibility of sustaining the traveller. Ocean navigators could fish. Arctic explorers could hunt. Astronauts in low Earth orbit receive abundant solar energy and can be resupplied within hours. The fundamental assumption behind every expedition in human history is that the environment through which one travels contains something usable. Interstellar space completely breaks this premise. It contains nothing that can be harnessed. The solar wind that propelled the journey has ceased. The sunlight that powered the instruments has faded into irrelevance. The surrounding interstellar medium, with its atom of hydrogen per cubic centimeter, cannot be collected in useful quantities, cannot be burned, and cannot be fused without such massive infrastructure that it would nullify its purpose. Any vehicle traveling through interstellar space must carry all its energy from departure to arrival. There is no recharge. There is no refueling. Now we come to the very distance itself. The closest stellar system to ours is Alpha Centauri, located about 4.24 light-years away. 1 light-year is approximately 9.5 trillion kilometers, which gives a total distance of about 40 trillion kilometers. Voyager 1, the fastest human-made object on a departure trajectory, travels at about 17 kilometers per second. At this speed, the trip to Alpha Centauri would take approximately 73,000 years. 73,000 years. When that journey would have begun, anatomically modern humans were painting on the walls of caves in Europe and sharing the continent with Neanderthals. Every civilization that has risen and fallen on Earth, every empire, every religion, every scientific revolution, every war, and every work of art fits comfortably within that span of time, and there would still be room. The entire recorded history of humanity, about 5,000 years, represents less than 7% of a single journey to the nearest star at our current speed. Can we go faster? The Parker Solar Probe, during its closest approaches to the Sun, reaches speeds of about 192 kilometers per second, the fastest man-made object relative to our star. If a spacecraft could maintain that extraordinary speed on an interstellar trajectory, the journey to Alpha Centauri would still take about 6,600 years. The ancient Sumerians were inventing cuneiform writing about that time. To reduce the transit time to something closer to a human lifetime, speeds nearly inconceivably fast are required. At 10% of the speed of light, about 30,000 kilometers per second, the trip to Alpha Centauri would take about 42 years. A crew leaving at 20 years old could arrive at 60. At 20% of the speed of light, the journey would be reduced to 21 years. But the energy required to reach those speeds is functionally absurd by current standards. The kinetic energy of an object scales with the square of its speed. Doubling the speed quadruples the energy required. To accelerate a modest payload of 1,000 kilograms, the weight of a small car, to 10% of the speed of light, would require about 4.5 times 10 to the 17th power joules of kinetic energy. That's equivalent to over 100 megatons of TNT, more than double the power of the Soviet Tsar bomber, the most powerful nuclear device ever detonated. And that calculation only accounts for the payload, completely ignoring the mass of the propulsion system, fuel, shielding, life support systems, and structure. For a ship weighing 100,000 kilograms, a modest mass for any vessel that could support a crew for decades, the energy required to reach 10% of the speed of light would be equivalent to tens of thousands of megatons of TNT. The total energy production of human civilization in a year is approximately 5.8 times 10 to the 21st power joules. Accelerating a single modestly sized starship would consume a significant fraction of all the energy the world produces annually, concentrated into a single propulsion event. These numbers also assume perfect efficiency, which no real system achieves. Each stage of energy conversion into motion introduces losses. A rocket engine converts chemical or nuclear energy into heat, the heat into expanding gases, the expanding gases into thrust, and thrust into speed. Each conversion loses a fraction of the total available. For a decades-long journey, these accumulated losses, combined with the energy required to sustain life support systems, computing, communications, and active shielding, further increase the total requirements. Chemical rockets, the pillars of current space exploration, have escape velocities of just a few kilometers per second, desperately inadequate. Ion engines achieve higher escape velocities but produce minimal thrust, requiring decades of continuous operation to accumulate significant speed. Thermonuclear rockets improve upon chemical performance but still fall short. Nuclear pulse propulsion, the idea of detonating atomic bombs behind the ship to be propelled by shockwaves, could theoretically reach a few percent of the speed of light, but it requires thousands of nuclear detonations and poses engineering challenges that have never been explored beyond preliminary studies. Nuclear fusion propulsion offers the most plausible path to interstellar speeds. The fusion of deuterium and helium-3 releases energy with an efficiency roughly 100 times greater than fission. A fusion-powered ship could theoretically reach between 5 and 10% of the speed of light. The problem: controlled fusion propulsion does not exist. Humanity has been working on controlled fusion for over 70 years and still has not achieved a net energy gain sustained in a terrestrial reactor, let alone a compact and reliable engine for a spacecraft. Another concept that captured the imagination of engineers during the second half of the 20th century is the laser sail, an extremely thin and lightweight membrane propelled by a beam of light or microwaves emitted from the solar system. Unlike propulsion systems that must carry their fuel with them, the sail receives its momentum from a fixed source. The Breakthrough Starshot project, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes sending gram mass sails to speeds of 20% of the speed of light using gigawatt laser beams. The calculations are physically plausible for milligram payloads, but scaling the concept to something capable of carrying useful scientific instruments, let alone living beings, requires overcoming engineering challenges in materials, optics, and energy management that remain unsolved. In 1960, physicist Robert Bussard proposed a seductive solution. Instead of carrying fuel, the ship would collect it directly from the interstellar medium, channeling hydrogen into an onboard fusion reactor. If it worked, the ship could accelerate indefinitely, feeding off the very vacuum through which it travels. Physics destroys this vision. With a typical density of 1 atom per cubic centimeter, collecting a single gram of hydrogen per second requires a collector with a cross-sectional area of tens of thousands of square kilometers. And later calculations following Bussard's original proposal revealed that the resistance generated by interacting with the medium at relativistic speeds would likely exceed the thrust generated by fusing the collected hydrogen. The interstellar medium is too empty to function as fuel and too present to be ignored as an obstacle. Bussard's stator reactor becomes a brake. Even if the propulsion problem were miraculously solved, the journey itself presents dangers that amplify with the time spent. Cosmic radiation permeates interstellar space at its full galactic intensity, an incessant bombardment, without shielding, coming from all directions. Within the heliosphere, the solar magnetic field deflects a significant fraction of the lower energy cosmic rays. Outside the heliopause, that protection disappears completely. Any crew would face a cumulative radiation dose that would increase relentlessly over the years and decades of transit. Studies on astronauts aboard the International Space Station who orbit under the partial protection of Earth's magnetosphere, already reveal measurable biological effects after only months of exposure. An interstellar journey lasting decades would magnify these effects in a dramatic way. Shielding reduces the dose, but does not eliminate the threat. Hadronic cascades triggered by a single cosmic ray inside the hull material can paradoxically cause a thicker shield to increase the total dose inside. Radiation and propulsion are trapped in a zero-sum competition for the mass of the spacecraft. Every kilogram of added shielding is one more kilogram that must be accelerated to interstellar speeds, aggravating the already monumental energy requirements. Add to this the complete absence of intermediate stopping points. Between our solar system and the Alpha Centauri system, there are no planets, no asteroids, no comets, no stations, no objects of any kind that could serve as a refuge, a reference point, or a resource depot. The Oort cloud, if it exists as theorized, may extend from our Sun to 1 or perhaps 2 light years. But its objects are small, extremely sparse icy bodies with separations of billions of kilometers between them, and they are not conveniently grouped along trajectories of departure. Even if a ship were to encounter one, the encounter would be brief, and the object, a dirty snowball a few kilometers in diameter drifting in the dark, would offer little practical value. Beyond the Oort cloud lies the true desert, 2 or 3 light years of space that current astrophysical models predict to be completely devoid of any solid bodies of significant size. Try to imagine how that absence of features would feel from inside a spacecraft. In the first months of the journey, the sun would remain the brightest object in the sky behind them, gradually dimming. Alpha Centauri would slowly shine ahead, although its increase in intensity would only be noticeable over years. Between those 2 reference points, the field of stars would remain fundamentally static. No object would appear to approach or recede at a speed perceptible to the human eye. No reference point of any kind would break the monotony. A crew member looking out the window on day 100 of the journey would see exactly the same stars in the same positions as on day 1000. This sensory deprivation would persist for years. At 10% of the speed of light, the most optimistic plausible cruising speed, the trip to Alpha Centauri takes over 4 decades. For the vast majority of that time, the surrounding environment provides no visual feedback of progress. The human brain is wired to interpret stillness as stagnation. The sense of a journey depends on changing landscapes, on reference points left behind. Interstellar space offers none of these vital cues. A crew that has traveled for 10 years at breakneck speed would look out the window and see a sky identical to the one they saw when they left. The psychological burden of this relentless monotony, sustained over decades in a confined spacecraft, with no option for shore leave, no possibility of turning back, and no guarantee that the destination will be hospitable, is a challenge that no human expedition has ever faced on anything remotely comparable in scale. The absence of stops also means the total impossibility of resupply. Every molecule of water, every kilogram of food, every spare part, every calorie of energy for the entire journey must be on board at the time of departure. A serious failure in deep interstellar space cannot be addressed by a rescue mission. The nearest help is light years behind and light years ahead. The very concept of an emergency, which in any other context of human experience implies the possibility of rescue, or at least withdrawal, loses all meaning definitively. And the situation with communications exacerbates this isolation in ways that cruelly develop over time. At launch, a spacecraft leaving the solar system would maintain near real-time communication with Earth. At 1/10 of a light year, The one-way delay would be 37 days. A question sent to Earth would receive a response more than 2 months later. At 1 light year, each message takes a year to arrive, a round trip of 2 years for a single exchange. At 2 light years, the midpoint of the journey to Alpha Centauri, the total delay exceeds 4 years. A child born on Earth when a message was sent would be starting school when the response reached the ship. The conversation hasn't slowed down. It has ceased to function as such in any practical sense. The intensity of radio transmissions diminishes with the square of the distance. NASA's Deep Space Network, with its antennas up to 70 meters in diameter, can maintain contact with probes at the heliopause. At interstellar distances, even these systems would face insurmountable difficulties. Maintaining a data link to a light year away would require vastly more powerful transmitters on board, consuming precious energy reserves, or receiving networks on Earth of colossal size, spanning kilometers instead of meters. During the final years of a journey, the crew would exist in a state of communicative isolation, unprecedented in human history. Messages from Earth would arrive years after being sent, carrying news of a world that has moved on without them. Responses sent from the ship would not reach Earth until long after the journey has concluded. For all practical purposes, the crew would be alone. Not with the romantic solitude of an explorer on a remote mountain, with the absolute solitude of being the only conscious beings within light years, separated from any other human by an abyss of space and time that no signal can cross quickly enough to matter. All of these constraints apply to the simplest possible interstellar journey, an expedition to the nearest star. The distances to other stars increase rapidly, and each difficulty compounds cumulatively, making each additional light year qualitatively more devastating than the last. Within a radius of 10 light years from the Sun, there are approximately 12 known stellar systems. Barnard's star, the next closest after Alpha Centauri, is 5.96 light years away. Wolf 359 is 7.86. Lalande 2 1185 is 8.31. Sirius is 8.6. A journey to Barnard's star at 10% of the speed of light would take approximately 60 years instead of 42. Those 18 additional years demand 18 more years of food, water, air, and energy. 18 more years of exposure to cosmic rays. 18 more years of material degradation and electronic fatigue. 18 more years of psychological endurance in a confined and unchanging environment. 18 years during which a single failure in a critical system could be fatal with no chance of external assistance. At a distance of 10 light years, the transit time extends to a century. 100 years aboard a spacecraft. No human has lived that long. A journey of this duration would require either technologies that do not exist today, such as reliable suspended animation, or a fundamental rethinking of the mission as a generational enterprise. A ship designed not for a crew that departs and arrives, but for a population that lives and dies aboard, with their descendants completing the journey. Generation ships introduce their own cascade of difficulties. Maintaining a stable and functional society for a century in a closed environment with finite resources and zero external inputs is an unprecedented social engineering challenge. Every calorie must be produced aboard. Every birth must be balanced with available resources. Every dispute must be resolved with no option for anyone to leave. The ship becomes an autonomous world, a sealed terrarium that must sustain human civilization across generations while traveling through a void that offers no help and forgives no mistakes. At 20 light years, the transit time at 10% of the speed of light reaches 2 centuries. At 50 light years, 5 centuries. At 100 light years, a millennium. And these are not distances to dark stars in remote corners of the galaxy. They are the distances to our closest stellar neighbors within our own arm of the Milky Way. The galaxy itself stretches across 100,000 light years. At 10% of the speed of light, crossing it would take 1 million years. Even traveling at the speed of light itself, an impossibility for any object with mass, the journey would require 100,000 years, a span approximately equal to the entire existence of anatomically modern humans on Earth. A journey to a star 50 light years away would involve spending 5 centuries in interstellar space, 500 years of exposure to cosmic rays, 500 years of wear on equipment, 500 years recycling the same air, the same water, the same finite materials, 500 years during which a message sent home would take a century to receive a response. The crew that departed would become legend, mythological figures for the descendants who would eventually arrive, if any did. And the nature of the medium never changes. At 50 light years, the density is still 1 atom per cubic centimeter, just like it is at 4. The cosmic ray flux is the same. The magnetic field does not vary. The absence of shelter, resources, and landmarks is total. The interstellar medium offers no oasis or resting zones. Its desolation is uniform across distances that span millions of potentially habitable worlds, each separated from its neighbors by this same unrelenting desert. The galaxy is so vast that interstellar space stops being a challenge and becomes a cage. The distances are not merely inconveniences. They impose structural isolation. Each star system exists as a tiny sphere of heat, energy, and protection, surrounded by a medium that offers nothing to those attempting to cross the abyss. The vacuum has no defenses because it doesn't need them. Its weapon is not force, but absence, the slow accumulation of nothingness across such vast distances that time itself becomes the enemy. This barrier is not a technological obstacle. It is geographical in the deepest sense of the word. It is the very shape of the galaxy, the structure of the space between the stars. The physical fact that most of the Milky Way is made of something that functionally is nothing. Let's now take a step back, beyond the spacecraft, engineering, and calculations of speed and energy. Let's momentarily forget the question of whether humans could cross the interstellar void. Instead, let's ask something more fundamental. What is the Milky Way physically when measured not by its shining points, but by its total volume? The answer is the most important conclusion of this entire story. The Milky Way disk has a diameter of approximately 100,000 light-years and an average thickness of about 2,000 light-years. It is within this disk that the majority of stars, gas, and dust are concentrated. Above and below stretches the galactic halo, a diffuse spherical region populated by ancient globular clusters, scattered stars, and an enormous envelope of dark matter that extends at least 130,000 light-years from the galactic center. Even if we confine ourselves to the disk, the total volume is staggering. A cylinder 100,000 light-years in diameter and 2,000 light-years thick contains approximately 15,000 million cubic light-years of space. Now let's consider how much of that volume is occupied by stars. Our Sun has a diameter of approximately 1,400,000 kilometers. In light-year units, that's just 0.000015 light-years. Even the largest known supergiants, such as VY Canis Majoris or Stephenson 2-18, measure only a tiny fraction of a light year in diameter. Stars are extraordinarily small compared to the spaces that separate them. In the solar neighborhood, the average distance between adjacent stars is about 4 to 5 light years. Each star occupies an average private volume of approximately 70 to 80 cubic light years. Within that volume, the star itself, even with a generous estimate of its physical size, occupies such a small fraction that it requires scientific notation to express it. The ratio between the volume of a typical star and the space it occupies is on the order of 1 part in 10 to the 22nd power. Written another way, it's a 1 followed by a decimal point and 21 zeros. It's roughly the same ratio as a single pebble compared to the volume of the entire Earth. If we could sum the volume of each of the 200 to 400 billion stars in the Milky Way, the total stellar volume would occupy less than 1/1000th of 1% of the total volume of the galaxy. The rest, the other 99.999999%, is interstellar space. This figure is not a pedagogical abstraction. It is a literal description of the galaxy's physical structure. If we could take all the matter from all the stars in the Milky Way, every hydrogen atom, every iron nucleus, every photon trapped in the stellar interiors, and compress it into marble-sized objects randomly distributed within the galactic volume, those marbles would be so spaced apart that if you were standing next to one, the probability of seeing the next one with the naked eye would be virtually zero. The gas at 1 atom per cubic centimeter, the magnetic fields of a few microgauss, cosmic rays flowing silently in all directions, dust grains separated by distances greater than entire city blocks. The galaxy is not a metropolis of stars with gaps between them. It is an ocean of interstellar medium where stars float like pollen grains drifting in a lake. The grains are real. The lake is what defines the environment. If we selected a random point anywhere within the volume of the Milky Way, the probability that this point would fall inside a star, or even within an astronomical unit of a star, is so close to zero that it would practically never occur. The overwhelming certainty is that this point would fall in interstellar space, surrounded by nearly absolute vacuum in all directions, with the nearest star as a faint point of light several light years away. This statistical reality is completely obscured by the way humans observe the galaxy. When we contemplate the Milky Way stretching across the night sky, we see stars, thousands with the naked eye, billions through telescopes. The visual impression is one of abundance, even of clustering. But this impression is a projection artifact. We are collapsing a 3-dimensional structure of thousands of light years of depth into a 2-dimensional image on our retina. Stars that are actually separated by vast abysses of empty space appear to overlap when viewed through the disk. The apparent density is an illusion created by the geometry of our observation. There is a way to break this illusion and see the volumetric reality more clearly. Compare the appearance of the Milky Way when you look directly into the galactic plane, where the depth of field is thousands of light years and the accumulation of stars creates the familiar bright band, with how it appears when you look perpendicularly to the plane, toward the galactic pole. In that direction, you're looking through barely 2,000 light years of disk, and the sky becomes noticeably less dense with stars. That perceptual difference between two viewing axes reflects the difference between projecting thousands of light years of depth and projecting just 2,000. Even that difference does not show you the true void. What you're collapsing in both cases is 3 dimensions into 2, and no 2-dimensional projection can reveal the true ratio of void to matter within that depth. If we could see the galaxy from the outside, from a privileged position millions of light years away and with eyes capable of resolving individual stars, the truth would be immediately apparent. The spiral arms would appear as faint luminous swirls against a background of almost total blackness. The gaps between individual stars would be visible as vast dark regions dotted with isolated points of light. The overall impression would not be of a dense, bustling structure. It would be of an overwhelming emptiness interrupted by very sparse light sources. The galaxy would reveal its true nature: sparse, solitary, a structure defined not by its matter, but by the void that contains it. This perspective applies not only to the Milky Way, but to every spiral galaxy in the observable universe. Andromeda, with its trillion stars, follows the same mathematics. The Triangle Galaxy, the Whirlpool Galaxy, every large spiral and every modest irregular dwarf, all are volumetrically dominated by the void. Stars are always outnumbered by the space surrounding them. The interstellar medium is the dominant reality. Even within the Milky Way itself, the distribution is not uniform. The spiral arms are denser than the intermediate regions, and the galactic center is more populated than the outer disk. But even in the densest parts of the galaxy, even within the bright spiral arms we see in images of other galaxies, most of the volume is still interstellar space. A spiral arm increases the local stellar density by a factor of 2 or 3 compared to the baseline between arms. Significant for star formation rates, but without changing the fundamental nature of the environment. The spiral arms are not permanent physical structures like tree branches. They are density waves, regions where gas and stars are temporarily compressed as they pass through a gravitational disturbance that rotates around the galactic center more slowly than the stars themselves. Stars pass through the spiral arms like cars pass through a construction zone on the highway. The traffic jam stays in the same place while the individual cars pass and move away. The Sun itself has entered and exited the Milky Way's spiral arms multiple times throughout its existence, and it will do so again. The apparent permanence of the spiral structure is a property of the wave, not the matter that crosses it. Above and below the galactic plane, the situation becomes even more extreme. Ascending a few thousand light years, one enters the lower regions of the galactic halo, where the interstellar medium thins even further. The stellar population consists mainly of ancient stars from globular clusters and scattered field stars, relics of the galaxy's earliest eras. The distances between these stars can be colossal. Tens or even hundreds of light years of near-perfect vacuum separating one faint red sun from the next. The halo is the interstellar medium in its most absolute expression. All of this leads to an inescapable conclusion. The hostility of interstellar space is not a localized danger, not a risk zone that a future traveler could learn to bypass by finding a safer route. There is no safer route. The interstellar medium is everywhere. It fills the spiral arms and the voids between them. It extends above and below the disk. It occupies the halo. It extends between every pair of neighboring stars in the galaxy without exception. There is no corridor through the Milky Way that avoids the thin gas, cosmic rays, magnetic fields, functional vacuum, and light-year distances. These conditions are not traits of a particular region. They are the characteristics that define the galaxy as a whole. The interstellar medium doesn't care how advanced the civilization trying to cross it is. A species 1,000,000 years older than humanity, with technologies so sophisticated that they would seem indistinguishable from magic, would still face the same atom per cubic centimeter, the same flow of galactic cosmic rays coming from all directions, the same absence of matter, energy, and shelter between one star and the next. Technology can build faster ships. It can design better shields. It can extend the duration during which biological or mechanical systems can function under hostile conditions. But it cannot change the medium itself. The interstellar gas does not become denser for a more advanced traveler. Cosmic rays do not politely reduce their intensity in the face of a civilization that has mastered nuclear fusion. The distances do not shorten because the species trying to cross them has spent 100,000 generations traveling through space. The barrier is not technological. It is geographical in the deepest sense of that word. As we write, 2 objects built by human hands continue their silent journey through the medium we've been describing. Voyager 1 and Voyager 2 are still transmitting from interstellar space, although their energy reserves are steadily dwindling. They are the only human-made artifacts that have crossed the heliopause, the only instruments that have directly experienced the environment we've described. And their own story of decay is, in itself, a lesson about what it means to exist beyond the reach of any star. Each spacecraft is equipped with a radioisotope thermoelectric generator powered by the decay of plutonium-238. The principle is elegantly simple. Plutonium decays radioactively, generating heat, and that heat is converted into electricity via thermocouples, semiconductor junctions that produce an electric current when there is a temperature difference between their 2 ends. There are no moving parts, no combustion, no dependence on sunlight, just the slow and unstoppable decay of a radioactive isotope converting mass into energy according to the most famous equation in physics. At launch, in 1977, each generator produced about 470 watts of electricity, a modest amount even by household standards, enough to power 4 or 5 incandescent light bulbs, but suitable for the scientific instruments of the era. The problem is the word unstoppable. Plutonium-238 has a half-life of 87.7 years, meaning that roughly every 88 years, half of the remaining atoms will have decayed. This process cannot be stopped. The isotope cannot be recharged. The available power decreases continuously and irreversibly. These generators lose about 4 watts of electrical power each year, a figure that seems small, but, when accumulated over decades, represents an unrelenting drain. Scientists at the Jet Propulsion Laboratory have been systematically turning off instruments to conserve energy for priority measurements. The heaters that protect the equipment from the cold of deep space have been shut down one by one. The instruments still operational share power in shifts through an electronic triage system that decides which measurements are worth preserving as the energy budget inexorably shrinks towards zero. This gradual disconnection process has not been arbitrary. It has required genuinely painful scientific decisions. In 2019, the Voyager 2 team turned off the heater for the cosmic ray and charged particle instrument, a device that had been making continuous measurements for 42 years. The instrument's temperature dropped to nearly 50 degrees Celsius below zero. Engineers estimated that the instrument should not survive those temperatures, based on the original design specifications written decades before by engineers who could not have anticipated that the spacecraft would travel so far. Surprisingly, the instrument continued working. It had survived conditions for which it had not been designed because the actual materials, under the pressure of decades of operation in the vacuum of space, had proven to be more resilient than the laboratory specifications predicted. This unexpected tenacity of the Voyager instruments is a pattern that has repeated throughout the entire mission. the spacecraft were designed for a primary mission of 4 years, aimed at exploring Jupiter and Saturn. That they are still operating nearly 50 years later is not only a tribute to the conservative engineering of the 1970s, but also to the extraordinary durability of systems that have remained in the vacuum, far from the heat, humidity, vibrations, and corrosive agents that degrade equipment on Earth. It is estimated that by the mid-2030s, no spacecraft will have enough energy to operate even a single scientific instrument. Their transmitters will fall silent. The flow of data that has connected humanity with these explorers for almost half a century will cease forever. The last bit of information sent from interstellar space will reach the antennas of NASA's Deep Space Network, and then there will be silence. But that silence will not be the end of the journey. After their transmitters fall silent, both voyages will continue their trajectory for billions of years without any significant disturbances. There is no friction in interstellar space. There is no resistance to slow their movement. The spacecraft that today travels at 17 kilometers per second will continue traveling at that speed 1,000,000 years from now, 100 million years from now, with an accuracy that no human chronometer can measure. Only rare gravitational interactions with passing stars could marginally alter their trajectories over geological timescales. The voyages will become what astronomers call interstellar population bodies, solid objects drifting between the stars, not gravitationally bound to any. Objects like these must exist in vast numbers in the galaxy, ejected from their parent systems by gravitational interactions during planetary formation, but they are virtually impossible to detect with current technology due to their small size and lack of self-emission. When Oumuamua, the first confirmed interstellar object to pass through the solar system, was detected in 2017, its nature was intensely debated. Was it a rock, a fragment of solid nitrogen, even a natural solar sail? Its interstellar origin was undeniable. Its exact composition, still uncertain. The voyagers, in tens of thousands of years, will be objects of the same category, except we will know exactly where they came from, because we placed them there. Without active instruments, without signals to Earth, but not empty. Each spacecraft carries a gold-plated copper disc, a 30-centimeter disc with a thickness of just over 1 millimeter. It is not solid gold, which would have been too heavy, but a layer of gold thick enough to protect the copper surface from corrosion, since in the vacuum of interstellar space, there is no oxygen to oxidize the metal, but there are energetic particles and micrometeoroids that could damage an unprotected surface over millions of years. The choice of material was not aesthetic, it was engineering. On its surface, sounds and images were encoded using an analog groove system that can be read with a needle, following the same principle as a vinyl record. Digital encoding was not used, as its interpretation would require knowledge of the encoding standard employed. Instead, a physically self-explanatory system was used. The signal recorded in the groove directly represents the variations in the amplitude of the sound wave, or the light intensity of each line of the image. On the cover of the disc, instructions were etched in universal scientific notation, using the hydrogen atom's oscillation period as the unit of time, explaining how to play it and how to interpret the images. The design assumes that any civilization capable of finding the spacecraft will have enough physics knowledge to understand the notation, but it does not assume any prior knowledge of human technology. The content was selected by a committee chaired by the astronomer Carl Sagan. Greetings in 55 human languages, from Akkadian to Wu. Music ranging from Bach and Beethoven to Chuck Berry's blues and traditional songs from Azerbaijan, Georgia, Japan, Senegal, Peru, and dozens of other cultures. The sound of wind, rain, ocean surf, and birdsong. The sound of a kiss, a mother soothing a baby, the beat of the human heart. Photographs of humans in different ages and contexts, of animals, landscapes, and human structures like the Golden Gate Bridge and a highway at night. An image of the double helix of DNA. The selection process itself was an extraordinary philosophical exercise. What would represent humanity to an intelligence that has never seen any of what we are? What would a species choose of itself if it knew it was possibly the only record that would survive its existence? The committee debated whether to include information about war, disease, and suffering. In the end, they did not. Not because they wanted to hide human darkness, but because the space limitation on the disk required a choice, and they chose to show capabilities rather than flaws. A photo of a naked man and woman was included as a representation of human anatomy, a decision that generated public controversy at the time, and which, in hindsight, reveals more about the cultural anxieties of 1977 than about the content itself. These discs were designed as messages for any extraterrestrial intelligence that might one day encounter the spacecraft. The probability of such an encounter is realistically extraordinarily small, not impossible, not absurd, but extraordinarily small. Interstellar space is so incomprehensibly vast that two small drifting spacecraft without propulsion have an essentially zero chance of approaching another star system within a meaningful time frame. Voyager 1 is heading toward the constellation Ophiuchus, and in about 40,000 years, it will pass approximately 1.6 light-years from the star. Gliese 445, a red dwarf in the constellation Camelopardalis, whose projected position in the sky at that time will be in the direction of Ophiuchus from our current perspective. It will not get close enough for a gravitational capture. It will not get close enough to be detected by any technology we can currently conceive from that star. It will not interact with any object from that system in any measurable way. It will simply pass by. A speck of metal in an ocean of nothing. Voyager 2, on the other hand, is heading in a different direction in the sky, and in about 40,000 years, it will pass about 1.7 light-years from the star. Ross 248, another red dwarf, also at a distance that makes the encounter physically irrelevant. Both spacecraft will then continue their trajectory toward deep galactic space, with no specific destination, no force that will significantly alter their course, for periods of time so long that the history of humanity will seem like a blink. In 1,000,000 years, if the Sun still exists, and Earth still exists, and some descendant of humanity still exists, Voyager 1 will be about 70 light-years from the solar system. In 100 million years, it will be about 7,000 light-years away, roughly a quarter of the distance to the galactic center. In 1 billion years, if the galaxy has not undergone a major collision that alters trajectories, it will be 70,000 light-years away, near the opposite edge of the galactic disk. None of these numbers imply that it will reach anywhere in particular. Interstellar space is so vast that even at those timescales, the chance of a meaningful approach to any star system remains tiny. In 10 billion years, when the Sun has expanded as a red giant and then contracted into a white dwarf, when Earth has been swallowed, or at least sterilized, the Voyagers will still be traveling. They will then be the most enduring objects humanity has ever created, longer lived than any building, longer lived than any book or inscription in stone. probably longer lived than any form of life we have generated directly or indirectly. The aluminum and titanium of their structures will slowly degrade from particle impact over these timescales, and the gold disks will gradually lose their surface sharpness. But the metal will remain metal. The mass will remain mass. The trajectory will remain trajectory. The gesture itself, the act of including that disk, reveals something profound about human nature that no scientific analysis can fully capture. There is no pragmatic reason for placing those disks on the spacecraft. They don't improve science. They don't increase the probability of any measurable outcome. They added weight, which in space engineering is a real and measurable cost. They were included because the group of people who designed the mission felt that if this was possibly the first opportunity for communication between humanity and any other form of intelligence in the universe, that chance, no matter how remote, deserved to be taken seriously. That if someone, somewhere, at some point, found this spacecraft, they deserved to know that those who built it thought, felt, made music, and looked toward the stars with something that can only be called hope. That says something about us that cosmic rays and plasma densities cannot. That, in the face of the almost absolute certainty of eternal anonymity, in a universe that is 99.999999% empty and completely indifferent, we wanted to leave a mark, not to survive, not to be rescued, just so that someone would know we were here. Those two tiny spacecraft, drifting silently through a medium that doesn't know thus they exist, heading towards stars they will never reach, carrying disks that perhaps no one will ever read, are at once the most concrete proof of the hostility of interstellar space, and the most powerful argument that this hostility is not the final word. If this journey has changed your perspective, if the night sky now looks different, this is the kind of content you'll find on this channel. Science that doesn't simplify, stories that don't offer easy comfort, realities that deserve to be known in their true scale. Subscribe for the next expedition.